In this video, we're going to do an example that you can do after you've seen the ideal gas law. It's an ideal gas law and a collecting gas over water type of problem. So we'll go ahead and try that out. So again, only come to this after you've done the ideal gas law. So let's go ahead and try this out. So we have 0.0460 grams of unknown gas occupies 360 mils when collected over water at 20 degrees Celsius and an atmospheric pressure of 80.00 kPa. Calculate the molar mass of the gas. So first of all, we want molar mass of gas. So we know that the mass is equal to moles times molar mass. And if we want to find the molar mass of the gas, generally we go to your periodic table. The problem is you can't really go to your periodic table in this case because it's an unknown gas. So we could use our formula to find it. We could do that the molar mass is equal to the mass over number of moles. If you look carefully, we have the mass already. Mass is equal to 0.0460 grams. And we don't have the number of moles, but we could find the number of moles because we have a volume given to us. It's a gas. And we also have pressure given to us as well. So let's find the number of moles using our ideal gas law. PV is equal to nRT. So the number of moles would be equal to PV over RT. Now, we need to make sure we're using the proper values here. So we have our volume is equal to 360 mils or 0.36 liters, because it does have to be in liters. So then we also have a pressure. Now pressure, remember, we have to find this by doing our partial pressures because this is collected over water. So we actually did that in the previous example from our note. We said that we had the total pressure is 80 kilopascals, and the partial pressure of the gas plus partial pressure of the water is equal to that 80 kilopascals. So we went to find the temperature of the water, which was 20 degrees Celsius, and we found that the partial pressure at 20 degrees is 2.33. Take that away from the total pressure, and that gives us the pressure of the gas. So the pressure of our gas is 77.67 kilopascals. So pressure is 77.67 kilopascals. So we have 77.67 kPa multiplied by our volume of 0.36 liters over our temperature. Our temperature was also given to us. It's 20 degrees Celsius, but don't forget it has to be Kelvin. So 20 degrees Celsius plus 273.15, we get 293.15 Kelvin. So that's our temperature over here, 293.15 Kelvin. And then the last part is the R value. So the R constant, the gas constant, we can write all the units in so we can see them cancel out. So our gas constant is going to be 8.314 because we're dealing with kPa. How do we know that? So let's go take a look over here. So if we go to our unit calendar and we go to our data tables over here, we can find the gas constants provided to us with all the units. So we have it over here, liters, kilopascal, mole, Kelvin. So let's go ahead and write that in there. 8.314 liters, kilopascal, mole, Kelvin. Whoops, I should have saved some space there. So liters, kilopascal per mole, Kelvin, and it's 8.314. So this is all our information that we need to find the number of moles. Again, this came from the partial pressure of the dry gas. This is the volume of the gas that we collected. This is the temperature provided in the question in Kelvin, and this is our gas constant, 8.314 with the kPa there. So kPa cancels out, liters cancel out, kelvins cancel out, and we're left with moles at the end. And that's what we're looking for. We're looking for the moles of our gas produced. So we can do the 77.67 times 0.36 divided by 8.314 divided by 293.15, and we get about 0.011472442 moles of the unknown gas. So our last step is simply molar mass is equal to mass over moles, so mass over moles, which is going to be the 0.0460 grams over the 0.01147, so on and so forth, moles. I have all the digits in my calculator still. So 0.0460 divided by our moles gives us approximately 4.009608264 grams per mole, which is a molar mass. And we can say, we can go to a proper number of sig figs. So it looks like 2 sig figs would be the smallest number that we could use. Actually, it would be 1 sig fig because that's our temperature of water there. So 1 sig fig is the smallest number there because we technically did use it in our calculation. So we'd have to take that into consideration. So we'd say approximately 4 grams per mole. So this would be the approximate molar mass of our unknown gas. Now, the next part of the question is saying, based on that molar mass, so based on the molar mass that we found, which is approximately 4 grams per mole, what's the identity of our unknown gas? So there's a couple things you can do. You can firstly look at the diatomic ones and see if it makes sense. So for fluorine, the molar mass of fluorine on its own is 19. I'm not putting all my, it could, 19.00. But there's 2 there, so times 2, that's 38.00 grams per mole. So it probably wouldn't be fluorine. It just doesn't add up. It's too high. We could try hydrogen. So hydrogen is 1.01 times 2. That's 2.02 grams per mole. So that does not match our 4 grams there. So that wouldn't work either. We can go for helium. For helium, we get about 4.00 grams per mole. So this helium matches our molar mass that we calculated. So since molar mass of the unknown gas is 4 grams per mole, the most likely chemical formula for the gas is He. Now, you could also double check the CO2 just if you want to see. So remember, CO2, oxygen is 16. So there's 16.00. So there's times 2 there, plus 12.01. So that's going to be 44.01 grams per mole. And that's way too high. So it wouldn't be that either. So really, it comes down to that being helium. So that concludes our extension question for the ideal gas law and collecting gases over water. You can really truly do this once you've done the ideal gas law. It does require a little bit of thinking. It does put your molar masses into perspective and combines that concept with the ideal gas law as well. So molar masses combined with ideal gas law, and then an experimental component to it as well.